The primary objective of multiple regression is to ascertain the unique contribution of a given predictor while accounting for, controlling for, or holding constant, all of those are synonymous, the other predictors that are also in the model. And I think that the first thing we look at to determine those things is the B weight in the output. So we get the output from R, we look at each predictor's B weight, and with that B weight is an associated beta weight, which is just the standardized version. And in the output, we can see there's a standard error associated with each B weight. There's a t-test and a p-value. And in addition, by the way, we can ask R to provide us with two other things that are also associated with each predictor, and that's a partial and semi-partial correlation. And when those are squared, they are effect sizes that are associated with a given slope for a predictor. So each predictor has its own B weight, beta weight of course, standard error, t value, p value, and a semi-partial and partial correlation. It's important to know as well that when a B weight is significant, we know that that associated predictor is important to the model. And so it's contributing uniquely, it's increasing the accuracy of the model. And if we excluded it, we would have a poor fitting model. And so oftentimes we do a regression, we look at the B weights, and from there we make decisions about which predictors to keep and which to eliminate because they're not helping the model. So sometimes that happens depending on, of course, our research goals. And so if that B weight's significant, we know that that predictor is important. And if the B weight is significant, the partial and semi-partial correlations will also be significant. So all those go together. And so if one's significant, they all are. And so I'm going to give an illustration to show you how to think about the partial and semi-partial and the distinction between the two kinds of effect sizes. And the semi-partial one is the more important one, but I'm going to explain both. So the example I'm going to use is from, I think, an old field textbook. I don't think it's the one you currently have, but I posted the data set on SharePoint in case you're interested. In this case, we're trying to predict exam performance in a given class from first the anxiety that the students are experiencing prior to the exam, and then the number of hours that they studied. And specifically, we're going to look at the anxiety exam performance relationship or prediction controlling for the amount of studying that was done. Now, I'm arbitrarily choosing which is the focal one we're interested in versus the control variable. And control variable is simply a variable that we're going to include in the model because it's relevant, meaning it correlates with the DV. And we want to, be able to pick up the unique contribution that anxiety brings to performance. But it's helpful if there's a variable out there that correlates with the DV to include that as a control. At least this is the philosophy behind including controls, because it soaks up some of the unexplained variance in the DV. And to the extent that we can do that, it's easier, given there isn't too much multicollinearity, it's easier to pick up significance for the variables that we care about. Do they uniquely contribute? That question can be more easily answered when there is less unexplained variability. So that's the whole idea behind controls. And again, in this example, we'll focus on anxiety controlling for studying, but it's just as plausible that we could be focused on studying as the primary variable of interest and then have anxiety be the control. So that is, totally up to the researcher and what your questions are. It's important to note, you can play around with the data set, at your leisure if you want. It's not required. But anxiety contributes in a negative way to exam performance, meaning that the more anxiety you have, the less likely you are to perform well. So that B weight is negative. But the hours spent studying is positive, such that the more hours you spend prepping, the better you'll do. And so these predictors both predict uniquely, but in different directions, which can totally happen in our research. So let me go through what these sections mean, just to review. The E, I think, is easy to remember because it's the error or unexplained variability. That means the predictors in our model just aren't covering it, aren't predicting this part. If we added more predictors that are relevant, maybe we could, and make that unexplained variability go down, and that helps everything to be more likely to be significant, including the B weights, the partials and semi-partials. But in this case, we just have the two variables, and so this is the part that's unexplained. The A part is the unique contribution of studying to the DV that is not explained by the other predictor. And likewise, with anxiety, this B space is the unique contribution of anxiety. And then the C plus D is just the bivariate between study and anxiety, and I don't remember what that was, or even the direction. If it's negative or positive, you could run that if you want. And then remember, the C space is the overlap between the two predictors that's shared with the DV, and that's the problematic part because we don't know which variable to assign credit for contributing that part to the DV. So the larger that C space is, the harder things get in terms of determining unique variability explained, and I will show you how that works in the math and in the regression equation part, specifically the standard error of the B weights, in the next segment. So we'll get to that. So let's go into the partial squared and semi-partial squared. Again, these are effect sizes associated with each predictor. And for the semi-partial squared, let's go over that first because I think it's a little bit easier. And it's this proportion, by the way, memorize this conceptual part, the proportion of total variability in performance, whatever the outcome is, that is explained uniquely by anxiety or only by anxiety. And the proportion is this B space in the numerator, and the denominator is the E plus A plus C plus B. So it's the whole entire circle of variability in exam performance. So it's this B space again over the entire thing. That is the semi-partial squared. And so I want you to know the conceptual definition of the SR squared and then be able to draw this diagram and know what proportion it represents. Now, sometimes we don't care about the total variability being the baseline or the denominator of our proportion. Sometimes we only care about the proportion of exam performance that is not explained by the studying variable. So in this case, we have the same numerator, so the partial squared is the same numerator. It's B. The partial squared for anxiety is B over B plus E. The proportion of variability in exam performance when studying that variable, that control variable in this case, is partialed out of both performance and anxiety. And so this is just what I see. At least for this class, we focus more on semi-partials, but just know that there are two kinds of effect sizes for any given predictor. And one is out of the total of the DV, and the other is out of just a portion of the DV, specifically the portion of the DV that is not covered by the control. So, in other words, the control variable is partialed out of both. And so I gave this hilarious illustration to hopefully help you remember with the partial. It's like Cookie Monster comes and takes a big bite out of both. So the studying variable goes away completely because Cookie Monster devoured it. And so the way that I've seen most people articulate this in the research is the question that's answered by the partial squared is, what is the proportion of variability in performance that is explained by anxiety when controlling for studying? Now, that is the way that I've seen it articulated, and that is technically correct, but it's not quite as precise, I would say. I think it's more precise and proper to say it's the proportion of variability in performance explained by anxiety when we partial out the control from both the DV and the focal variable, in this case, performance and anxiety. So what does this mean in terms of the distinction between the size of an SR squared versus PR squared? A PR squared is going to be larger. It's going to be larger because it doesn't have as large a number in its denominator. It has a smaller number in its denominator, and given that the numerator is consistent across both, it's B in both cases of the SR squared and PR squared. Then the only difference is it's out of a different total. And in one case, the total is the entire exam performance variable. And then in the PR squared case, the partial squared case, it's only out of the E plus B space. So depending on your research question, you could have committee members, clients, whoever, ask you to provide one or both of these effect sizes. And hopefully, based on the knowledge that you learned from this class, you would be able to go back and review probably, and then be able to give them an answer. So this this slide is just, I think, actually, it's maybe a review of what we've already covered. So the SR squared is, again, the unique contribution of anxiety out of the total variability in the DV. So just keep talking it through. I would say the best way to practice is to keep talking through and just memorize it word for word, especially when you're learning. And then later, when you understand it really well and you feel more comfortable, you can take more liberty and explain it in different ways. So first step, word for word, keep practicing talking through the first, for example, the semi-partial squared is the proportion of total variability in the DV that is only explained or uniquely explained by the focal predictor, in this case, anxiety. And so, and then you can articulate as well the partial by saying it's the proportion of variability in performance explained by anxiety when the control variable or hours of studying is partialed out of both. And the way I've seen, by the way, before wrapping up, the way I've seen partial squared used most often, I think, is when we have just this three variable case, two predictors and one DV. And one predictor is the control and the other is the focal predictor. Once we get into hierarchical regression where we have maybe 5 controls and we enter them in the first step, and then we have a next step, we're entering our focal predictor of interest to understand how the R-squared changes across the two, which I'll get to here in a bit. That's when I don't see people talk about partials at all, and it's all about semi-partials. So I'm going to stop here, and don't worry if you still have questions about this, because I think some of them are going to be answered, if not all, in the upcoming segments.